good evening, and welcome to Dreamy Academy. Tonight, we drift far back through time, to when the earth breathed differently, when landscapes were painted with forms we can only imagine, and silence stretched across millions of years. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. There's a quiet wonder in simply existing, isn't there? In the gentle rhythm of your own breath, a subtle echo resonates across unimaginable spans of time. Consider this. Every single breath you take contains atoms that once flowed through the lungs of ancient creatures. Perhaps a towering sauropod browsing on prehistoric ferns, or a swift velociraptor scenting the air. The very air that fills your lungs is a tapestry woven from countless pasts, linking you intimately to a world that existed long before human memory. If you could watch the earth breathe across eons, continents would drift like rafts on a slow, molten ocean, colliding and reforming with the patience of geological time. Mountains would rise and erode like fleeting ripples, and oceans would advance and retreat, painting vast canvases of sediment. Within this immense, unhurried dance, life itself has played out its story, a narrative of astonishing complexity, resilience, and transformation. And the only way we can read this epic tale, the only way we can glimpse those ancient worlds, is through the silent, patient language written in stone, the language of paleontology. Paleontology is not merely the study of old bones. It is the art of reading Earth's most profound diary, a record etched in rock, whispering secrets of primordial seas, sun-drenched forests, and creatures beyond our wildest dreams. It is a field that rewards not speed, but contemplation, a gentle, unhurried journey into deep time, where the beauty lies not just in what we find, but in the sheer miracle of its preservation and the intricate connections it reveals between all life, past and present. To truly appreciate this beauty, we must learn to stretch our imagination, to allow the vastness of time to settle around us, not as a dizzying void, but as a rich, fertile ground for understanding. So, let us begin our quiet journey, drifting back through the eons, guided by the whispers in stone. Have you ever held a stone in your hand and felt its cool, quiet weight? Perhaps a smooth river stone, or a jagged piece of quartz. It seems utterly inert, an unyielding fragment of the earth. But what if that stone, beneath its silent exterior, held a story of ancient seas, of creatures long vanished, of the very fabric of life woven into its crystalline structure? This is the profound invitation of paleontology, to see not just rock, but a canvas upon which the immense narrative of Earth's living history has been painted, stroke by patient stroke, across billions of years. To find a fossil is to encounter a whisper from deep time, a tangible echo of a world that existed before human eyes ever gazed upon it. At its heart, a fossil is simply a trace of ancient life preserved in rock. But this simple definition belies an astonishing complexity, a dance between organic matter and mineral forces, played out over timescales that dwarf human comprehension. We often imagine grand skeletons, perfectly articulated and ready for a museum display. And while these are indeed magnificent, They represent only a tiny, fleeting fraction of what the Earth has preserved. Most organisms, when they die, simply vanish. They are consumed, decayed, scattered by wind and water, their delicate structures reclaimed by the relentless cycles of the living world. The conditions for fossilization are, in fact, remarkably rare. A convergence of circumstances that allows a whisper to persist across millions of years, transforming fragile life into enduring stone. To begin to understand this transformation, we must first truly grasp the concept of deep time. Our human lives unfold in seasons, years, decades, a blink in the Earth's existence. A single human lifetime, perhaps 80 or 90 years, barely stirs the dust of geological time. Imagine, if you will, the entire 4.5 billion year history of our planet compressed into a single 24-hour day. On this scale, the very first single-celled life appears only around 4 a.m. Dinosaurs don't arrive until after 10 p.m., and they vanish about 20 minutes later. The entirety of human civilization, from the first cave paintings to this very moment, flickers into existence in the last fraction of a second before midnight. This immense scale, this patient unfolding over eons, is the canvas upon which fossils are created, a testament to the slow, relentless power of geological processes. The journey from a living organism to a fossil typically begins with a swift, gentle burial. Imagine a fish swimming in a shallow sea. When it dies, its body might settle onto the seabed, where it is quickly covered by fine-grained sediment, perhaps mud, silt, or volcanic ash. This rapid burial is crucial because it shields the delicate remains from scavengers, currents, and the destructive power of oxygen, which fuels decay. Each layer of sediment settling upon the last is a page in a slow-moving diary, gradually accumulating, pressing down, and compacting the material beneath. Over vast stretches of time, as more and more layers build up, the weight of the overlying sediment increases, gently squeezing out water and compacting the buried remains. It is within these quiet, buried layers that the true magic of fossilization begins. One of the most common and beautiful forms of preservation is called permineralization. Picture a piece of wood or a bone buried deep within the earth. Over millennia, groundwater, rich with dissolved minerals like silica, calcite, or pyrite, seeps slowly through the porous remains. As this mineral-laden water permeates the empty spaces within the bone or wood, the tiny hollows where cells once resided, the microscopic channels that carried nutrients, the minerals begin to precipitate out of the water and crystallize. Slowly, patiently, these minerals fill every available pore, every microscopic cavity, effectively turning the organic structure into stone cell by cell without altering its original form. The original organic material might still be present, encased and protected, or it might be slowly replaced by the incoming minerals. The result is a faithful, stony replica, a perfect mineral cast of the original structure. This patient chemical replacement is a wondrous thing. Consider replacement, a related process where the original organic material of the organism is not just filled, but entirely dissolved away and replaced by new minerals. A shell, originally made of calcium carbonate, might be completely replaced by silica, maintaining every intricate curve and ridge, but now composed of a different substance entirely. The beauty of this process lies in its precision. The mineral solutions act as a microscopic sculptor, copying the original form with exquisite detail, transforming the ephemeral into the enduring. Beyond these stony replicas, fossils can take many other forms, each telling a unique part of the ancient story. Sometimes the buried organism simply leaves an impression in the surrounding sediment. If a shell, for instance, is buried and then later dissolves away, it leaves a hollow cavity in the rock, a mould. If this mould is subsequently filled with new sediment or minerals, it creates a three-dimensional replica of the original shell, known as cast. These moulds and casts offer a faithful external portrait, capturing the surface textures and shapes of ancient life, even when the original material has long since vanished. Even more evocative are trace fossils. These are not the remains of the organism itself, but rather the preserved evidence of its activity. Imagine a dinosaur walking across a muddy floodplain. Its heavy foot sinks into the soft earth, leaving a distinct impression. If that footprint is then quickly covered by another layer of fine sediment, and the conditions are right for fossilization, that momentary step can be preserved for millions of years. Trace fossils include not only footprints, but also burrows, feeding trails, nests, and even fossilized feces, known as coprolites. These quiet imprints offer a unique window into the behavior of ancient creatures, how they moved, how they fed, how they interacted with their environment. They are the echoes of movement, the preserved moments of daily life in a long-lost world. Then there are the delicate marvels of carbon films. When an organism, particularly a plant or a soft-bodied animal, is buried under fine sediment, the immense pressure and heat of burial can drive off all the volatile compounds, the hydrogen, oxygen, and nitrogen. What remains is a thin black film of carbon, a two-dimensional silhouette of the original life form, pressed flat onto the rock. These carbon films often preserve exquisite detail, revealing the delicate venation of ancient leaves or the intricate outlines of primeval fish, a ghostly portrait rendered in elemental black. Finally, there are the rare, extraordinary instances of exceptional preservation. Sometimes entire organisms are trapped in environments that prevent decay almost entirely. Insects perfectly preserved in amber, fossilized tree resin, offer a breathtaking glimpse into ancient ecosystems, their delicate wings and antennae frozen in time. Mammoths and other Ice Age creatures, entombed in permafrost, can retain not just their bones, but their skin, fur, and even soft tissues. Animals caught in tar pits, like those at La Brea in California, provide a rich assemblage of ancient fauna, their bones preserved by the asphalt. These exceptional finds are precious, offering a level of detail that other forms of fossilization rarely achieve, illuminating entire ancient worlds with startling clarity. So, what do these silent whispers in stone tell us? They are the undeniable evidence of evolution, showing us how life has changed and diversified over unimaginable spans of time. They reveal ancient geographies, telling us where oceans once lay, where mountains stood, and how continents have drifted. They paint pictures of past climates, from lush tropical forests near the poles to vast arid deserts. Each fossil is a piece of a grand, interconnected puzzle, allowing us to reconstruct not just individual organisms, but entire ecosystems, bringing vanished worlds back into focus. They teach us humility, reminding us of the immense age of our planet and the fleeting nature of our own existence within its vast timeline. And they inspire wonder, as we realize that the very rocks beneath our feet hold the preserved memories of life's long, patient journey. There's a particular comfort in understanding that the past isn't truly gone, but merely transformed, waiting patiently to be read. Looking back across those millions of years, we see not chaos but structure, not randomness, but a profound tapestry of cause and effect. The universe, it seems, has a tendency toward this kind of beautiful layered storytelling. So we've seen how life, in rare and precious moments, can leave its enduring mark in the silent language of stone. But how do we decipher these whispers? How do we know when these stories were written? How can we possibly assign ages in millions of years to a piece of ancient bone or a fossilized leaf? That quiet question of dating the distant past leads us deeper into the Earth's patient clockwork, revealing how scientists, with ingenuity and precision, have learned to read the very heartbeat of time itself. The whispers in stone, as we explored in our last quiet gathering, speak of lives lived long ago, of ancient seas and forgotten forests. They offer us glimpses, fragments of a vast and intricate story. But these whispers, however profound, do not arrive with a date stamped upon them. They do not carry a little tag proclaiming, "I am 150 million years old," or "I witnessed the dawn of multicellular life." And so, a fundamental question emerges from the tranquil depths of our inquiry. How do we, with our fleeting human lifespans, begin to grasp the chronology of these ancient echoes? How do we place these precious relics into the correct chapter of Earth's unimaginably long autobiography? To understand paleontology, you see, is not merely to discover a fossil. It is to understand its context within the immense tapestry of deep time. It is to learn to read the calendar inscribed not on paper, but in the very bedrock beneath our feet. This is the art and science of geochronology, the dating of Earth's history, and it is a cornerstone of our slow and thoughtful adventure. Imagine, if you will, a towering library. Each book is a layer of rock, and within these books the stories of life are penned. But these books are not neatly arranged by publication date. Some are jumbled, some are missing, and some have pages torn out or reordered. Our task as paleontologists is to bring order to this magnificent chaotic archive. We employ two primary methods, two distinct but complementary ways of telling time: relative dating and absolute dating. Let us first consider relative dating, a method that asks not, quote, 2, but rather, quote, 3. It is a logic born of observation, a common sense understanding of how layers accumulate. Think of a stack of laundry, perhaps, or a pile of newspapers. The item at the bottom was placed there first, making it the oldest, while the item at the top is the most recent. The Earth, in its grand, slow processes, follows a similar though far more complex principle. This principle is formally known as the Rast law of superposition, a foundational concept in geology first articulated by the Danish scientist Nicholas Steno in the 17th century. It states quite simply that in an undisturbed sequence of sedimentary rock layers, the oldest layers are at the bottom and the youngest layers are at the top. When we gaze upon a canyon wall, its multicolored strata exposed like the pages of an open book, we are seeing deep time laid bare. Each layer, or stratum, represents a period when sediments, sand, mud, volcanic ash, or the shells of marine creatures, were deposited, slowly accumulating over millennia. The fossil found in a lower stratum is by this law older than a fossil found in a higher stratum within the same sequence. It provides us with the foundational sequence, a conceptual ladder through time. But what if our rock layers are not so neatly stacked? What if they have been folded, faulted, or eroded away? Here, other principles of relative dating come into play. The principle of original horizontality reminds us that most sedimentary layers are originally deposited horizontally. If we find them tilted or folded, we know that geological forces acted upon them after their deposition. The Chesty principle of cross-cutting relationships tells us that if a fault or an igneous intrusion cuts across existing rock layers, then that fault or intrusion must be younger than the layers it cuts through. And then there are unconformities. Those enigmatic gaps in the geological record where erosion has removed vast stretches of time, creating a hiatus, a missing chapter in our stone book. Each of these principles helps us to reconstruct the original order of events, piece by careful piece. Beyond the physical arrangement of rocks, the fossils themselves become invaluable timekeepers in relative dating. This brings us to the concept of vernal index fossils. Imagine a particular species of ancient marine creature that lived for a relatively short geological period, was geographically widespread, and was abundant. If we find this specific fossil in a rock layer in North America, and then again in a rock layer in Europe, we can infer that those two geographically distant layers were deposited at roughly the same time. These index fossils act as distinctive markers, like specific editions of a newspaper that tell us not the exact day, but at least the month or year of its printing. They allow us to correlate rock layers across continents, weaving together a global timeline. Closely related is the principle of faunal succession, which observes that fossil organisms succeed each other in a definite and determinable order, and therefore any given period of time can be recognized by its characteristic fossils. This isn't just about single index species, but about assemblages of life. The types of creatures found in one era are distinctly different from those found in another. We wouldn't expect to find a dinosaur alongside a trilobite, for instance, because their reigns on Earth were separated by vast stretches of time. This predictability in the appearance and disappearance of life forms allows us to establish a consistent sequence, a grand evolutionary parade march through the ages. Relative dating, then, gives us a profound understanding of sequence. This happened before that, and that happened after this. It allows us to build a magnificent, ordered narrative of life's progression, a grand storyline, but it does not provide us with numbers. It cannot tell us that a particular dinosaur lived 100 million years ago, only that it lived after the first mammals and before the first flowering plants. For those precise numerical ages, we turn to the second, more intricate method, absolute dating. Absolute dating is where the Earth itself becomes a magnificent ticking clock, powered by the subtle, unwavering forces of atomic decay. This method relies on the phenomenon of radioactivity, where certain unstable isotopes of elements spontaneously transform into more stable forms over time, releasing energy in the process. This transformation happens at a constant, predictable rate, unaffected by external conditions like temperature or pressure. It is, in essence, nature's most reliable stopwatch. Every radioactive isotope has a characteristic half-life. the amount of time it takes for half of the parent radioactive atoms in a sample to decay into stable daughter atoms. Imagine a jar full of tiny glowing particles. After one half-life, half of these particles will have changed colour and stopped glowing. After another half-life, half of the remaining glowing particles will have changed, and so on. By measuring the ratio of parent isotopes to daughter isotopes in a rock sample, scientists can calculate how many half-lives have passed since the rock formed, and thus determine its absolute age in years. Perhaps the most famous example of absolute dating is carbon-14 dating. Carbon-14 is a radioactive isotope of carbon that is continually produced in the Earth's upper atmosphere. Living organisms absorb carbon-14, along with stable carbon-12, from the atmosphere and their food. When an organism dies, it stops absorbing new carbon, and the existing carbon-14 begins to decay into nitrogen-14 with a half-life of about 5,830 years. By measuring the remaining carbon-14 in organic remains like wood, bone, or shells, we can date events up to around 50,000 to 60,000 years ago. This makes it incredibly useful for dating recent archaeological finds and the remains of early humans. But it is far too short-lived to date the vast ages of dinosaurs, or the earliest forms of life. For the deep, deep past, we turn to isotopes with much longer half-lives, often found within igneous rocks. Rocks formed from the cooling and solidification of molten magma or lava. Why igneous rocks? Because when magma cools and minerals crystallize, they lock in a certain ratio of parent and daughter isotopes. The clock effectively starts ticking at that moment of crystallization. Sedimentary rocks, where most fossils are found, are made up of weathered fragments of older rocks, so dating the sediments themselves would give us the age of the source rocks, not the age of deposition. Instead, we often date the igneous layers that bracket the fossil-bearing sedimentary layers. If we find a volcanic ash layer above the fossil and another volcanic ash layer below it, we can date both igneous layers and determine that the fossil must be younger than the lower ash and older than the upper ash. This provides a numerical age range, a precise window in time for the fossil's existence. Consider potassium-argon, Kr, dating, or its more refined cousin, argon-argon, Ar dating. Potassium-40 decays into argon-40 with a half-life of 1.25 billion years. This makes it ideal for dating very old volcanic rocks, from hundreds of thousands to billions of years old. When volcanic rock forms, any argon-40 gas, which is inert, usually escapes, so the clock starts with virtually no daughter product. As the rock ages, potassium-40 decays, and the argon-40 daughter product accumulates, trapped within the mineral crystals. For even more ancient rock formations, we might employ uranium-lead, UPB, dating. Uranium isotopes, uranium-238 and uranium-235, decay through a series of steps into stable lead isotopes, lead-206 and lead-207 respectively. These decay chains have incredibly long half-lives, extending into the billions of years, making them perfect for dating the oldest rocks on Earth, including tiny resilient crystals called zircons, which can preserve a record of Earth's earliest crust. These absolute dating methods, while numerically precise, are not without their complexities. They require pristine samples, careful laboratory analysis, and a deep understanding of geological processes. Yet, when applied thoughtfully, they unlock the numerical secrets of Earth's history. So, you see, relative dating provides us with the sequence, the narrative flow, the understanding of before and after. Absolute dating provides the specific numerical dates, the chapters and page numbers, anchoring that narrative to a precise timeline. They are not competing methods, but rather two indispensable lenses through which we view the grand unfolding of deep time. They are two threads, woven together with meticulous care, creating a robust and incredibly detailed chronological fabric. It is through this masterful combination of relative and absolute dating that we have been able to construct the geological timescale, that magnificent calendar of Earth's history. It is a testament to human ingenuity and perseverance, allowing us to map the rise and fall of continents, the ebb and flow of ancient oceans, the profound shifts in climate, and most wondrously, the spectacular branching tree of life itself. We can now say with confidence that the dinosaurs walked the Earth between approximately 230 and 66 million years ago, that the first multicellular life appeared over 600 million years ago, and that our planet itself coalesced from cosmic dust around 4.54 billion years ago. This understanding of time is not merely an academic exercise. It is a profound journey into our own origins. Every single breath you take contains atoms that have been cycled through countless ancient organisms, through the very air breathed by trilobites, by dinosaurs, by early hominids. We are quite literally made of stardust and deep time, and by learning to read Earth's grand clockwork, we are not just dating rocks, we are dating ourselves, our lineage, our place in the vast, awe-inspiring continuum of existence. As we move forward, let us carry this sense of profound connection, this appreciation for the meticulous work that allows us to peer back into the abyss of time. For with these tools of dating in hand, we are now truly ready to embark on a more detailed exploration of the epochs, eras, and periods that define the story of life on Earth, to truly understand the chapters of that magnificent stone-bound autobiography. With our understanding of Earth's grand clockwork now established, with the relative sequences and absolute dates woven together, we arrive at one of the most magnificent constructs of scientific endeavour, the geological time scale. It is not merely a chart, you see, but a narrative, a vast and intricate tapestry woven from countless pasts, stitched together by the patient hands of countless scientists across generations. It is Earth's most profound diary, its pages inscribed not with ink, but with the very rock and fossil record we have learned to read. Imagine, if you will, that we are holding a single ancient volume in our hands, a tome so immense that its pages encompass billions of years. This book is the history of our planet, and the geological time scale is its meticulously crafted table of contents, allowing us to navigate its epic story. It is a testament to the fact that while time flows relentlessly forward, its passage leaves indelible marks, allowing us to look back, to reconstruct, to truly see the journey of life and land. We speak of quote, and it is here, within the architecture of the geological timescale, that this concept truly takes form. It is a framework, yes, but also an invitation to humility, a quiet reminder of our fleeting presence against a backdrop of cosmic scales. This scale is divided into hierarchical units, much like a library organizes its knowledge. The largest divisions are the eons, vast stretches of time representing fundamental chapters in Earth's history. These eons are further subdivided into eras, which in turn contain periods, then epochs, and finally the most granular units, ages. Each division is not arbitrary. It marks a significant shift, a global event, a profound change in life or the planet itself. Let us begin our gentle stroll through these eons, these primordial chapters. The very first, the Hadean Eon, stretches from Earth's formation, some 4.6 billion years ago, to about 4 billion years ago. Its name, derived from Hades, speaks volumes. This was a time of unimaginable violence, a truly hellish landscape. Our nascent planet was a molten sphere, constantly bombarded by asteroids and comets, a cosmic forge where the very elements of our world were still settling. There were no continents, no oceans as we know them, only a searing gaseous atmosphere and a surface that glowed with residual heat. We find no fossils from the Hadean, for life itself had not yet begun its tentative stirrings. It was a time of foundation, of the earth finding its form, cooling its fiery heart, beginning the long process of differentiation that would give us core, mantle, and crust. It is a profound emptiness, a necessary silence before the symphony of life could even begin to tune. Following the Hadean, we enter the Archean Eon, from 4 to 2.5 billion years ago. The Earth breathes differently now. The relentless bombardment has lessened. The planet has cooled sufficiently for water vapour to condense, forming vast primordial oceans. And it is within these dark, mineral-rich waters that the miracle occurs, the spark of life. The Archean is the eon of the first life forms, simple, single-celled organisms, prokaryotes, akin to modern bacteria and archaea. They were microscopic pioneers, thriving in an oxygen-poor atmosphere, perhaps clustered around hydrothermal vents, drawing energy from chemical reactions deep beneath the waves. We find their faint traces as stromatolites, layered mounds of sediment and microbial mats, Earth's first architects, slowly, patiently, beginning to reshape the planet's chemistry, releasing oxygen as a waste product, unwittingly setting the stage for everything that would follow. The Archean is a testament to life's tenacity, its ability to emerge from the most extreme conditions, to find a foothold and begin its quiet, persistent work of transformation. Then comes the Proterozoic Eon, from 2.5 billion to 541 million years ago. This is the longest eon, a vast expanse of nearly 2 billion years, often called the Age of Invisible Life, yet it is anything but uneventful. Here, life makes its next monumental leap. We see the emergence of eukaryotes, cells with a nucleus and other complex organelles, a profound evolutionary innovation that would unlock the potential for multicellularity. The atmosphere, slowly enriched by billions of years of microbial photosynthesis, begins its transition to oxygen-rich, fundamentally altering the planet's surface and ocean chemistry. Continents would drift like rafts across the oceans, colliding and merging to form supercontinents, then breaking apart again in a slow, majestic dance. This eon also witnessed some of Earth's most dramatic climate shifts, including several snowball Earth events, where our planet was largely encased in ice, a testament to its dynamic, sometimes violent nature. Towards the very end of the Proterozoic, in what is known as the Ediacaran period, we find the first evidence of macroscopic, soft-bodied organisms, the Ediacaran biota. These enigmatic creatures, unlike anything alive today, represent the earliest known complex multicellular life, a strange and beautiful prelude to the explosion of biodiversity that was yet to come. They are ghostly portraits rendered in elemental black, impressions in ancient sands, whispering secrets of a world on the cusp of profound change. And finally, we arrive at the Phanerozoic Eon, which spans from 541 million years ago to the present day. Its name means visible life, and indeed, it is the eon during which complex, diverse, and abundant life forms, including ourselves, have flourished. This is the chapter of Earth's story that most people are familiar with, the time of shells and skeletons, of forests and fish, of dinosaurs and mammals. The Phanerozoic is further divided into 3 grand eras, each marking a distinct chapter in the unfolding drama of life. First, the Paleozoic era, from 541 to 252 million years ago. This era begins with the Cambrian explosion, an astonishing burst of evolutionary innovation where most major animal phyla suddenly appear in the fossil record. Seas teemed with trilobites, brachiopods, and the first fish. Life colonized the land, first as plants, then as amphibians and the earliest reptiles. The Paleozoic was a time of grand diversification, of the forging of ecosystems, only to culminate in the most catastrophic mass extinction event in Earth's history, the Permian-Triassic extinction, often called the Great Dying, which wiped out an estimated 90% of marine species and 70% of terrestrial vertebrate species. It was a stark reminder of Earth's power, its capacity for both creation and profound destruction. Next, we journey into the Mesozoic era, from 252 to 66 million years ago, famously known as the quote, 8. This is the era when dinosaurs reigned supreme, dominating terrestrial ecosystems for over 160 million years. Mammals made their first appearance, small and unassuming, living in the shadows of their reptilian overlords. Birds evolved, taking to the skies, and flowering plants began to diversify, transforming landscapes with their vibrant colours and scents. The Mesozoic was a time of shifting continents, of warmer climates, of a world that would feel both alien and strangely familiar. This era, too, ended abruptly with another significant mass extinction event, widely attributed to a massive asteroid impact, which brought about the demise of the non-avian dinosaurs and many other life forms. And finally, the Cenozoic era. From 66 million years ago to the present. This is our era, the quote 9. With the dinosaurs gone, mammals diversified rapidly, filling the ecological niches left vacant. Birds too underwent a spectacular radiation. Continents continued their slow drift to their present positions, and the Earth's climate cycled through periods of warmth and glaciation. It is within the Cenozoic that primates evolve, eventually leading to the emergence of Homo sapiens. Our own story, the story of humanity, is but the blink of an eye in this immense Cenozoic chapter, a mere whisper in the grand narrative of the Phanerozoic. Consider this vast expanse of time, these eons and eras, not as abstract numbers, but as living, breathing epochs, each with its own unique cast of characters, its own landscapes, its own triumphs and tragedies. The geological time scale is our key to unlocking these worlds. It allows us to place every fossil, every rock layer, every ancient whisper into its proper context, to see its relationship to what came before and what followed. It is the very framework that transforms isolated discoveries into a coherent, interconnected story of life's enduring journey. We stand now, you and I, at the precipice of understanding not just what happened, but when it happened, and how each moment built upon the last. This chronological scaffolding is indispensable. For without it, paleontology would be a collection of fascinating but disconnected curiosities. With it, we gain perspective, a profound sense of belonging to this continuous unfolding story. We are not separate from this deep time. We are its most recent expression, a fleeting moment born from billions of years of geological and biological evolution. So let us carry this grand framework in our minds, this map of Earth's history, as we prepare to delve deeper into specific periods to meet the creatures that once roamed these ancient lands and swam these primordial seas. The geological timescale is our compass, guiding us through the immense ocean of time, promising further wonders and deeper insights into the fundamental questions of life itself. It reminds us that every single breath you take contains atoms that have been part of this planet since the Hadean, that the very ground beneath your feet holds secrets from the Archean, and that the pulse of life that animates you is a direct descendant of the hardy pioneers of the Proterozoic. We are, truly, made of stardust and deep time. We have journeyed through the immense corridors of deep time, charting Earth's biography through its geological epochs, eras, and eons. We have seen how the planet itself has transformed, from a molten infant to a vibrant living sphere, its continents drifting like rafts upon a slow-moving ocean of mantle, its atmosphere shifting from primordial haze to the breathable air we now share. And within this grand unfolding narrative, we have glimpsed the astonishing story of life, from the simplest single cells to the intricate complexity of the present day. But how, you might ask, does life navigate such vast stretches of time? How does it adapt to cataclysmic changes, to shifting climates, to the very rearrangement of continents? How do new forms emerge, flourish, and sometimes tragically vanish? The answer lies at the very heart of paleontology, woven into every fossil we uncover, every rock layer we interpret, the relentless, beautiful, and profoundly creative process we call evolution. Evolution is not merely a theory. It is the fundamental framework that explains the diversity of life on Earth, both past and present. It is the engine that drives the changes we observe in the fossil record, the sculptor that shapes species over countless generations. When we speak of evolution, we are speaking of descent with modification. The idea that all life is connected, sharing a common ancestor, and that over time species change, adapt, and diversify, giving rise to new forms. Let us pause for a moment to dispel a common misconception. Evolution is not a ladder of progress with humanity at its apex. It is not a directed march towards perfection. Rather, it is a branching bush, intricate and sprawling, where every twig represents a species and every fork in the branch a divergence from a common ancestor. Life does not strive for an ideal form. It simply responds to the ever-changing pressures of its environment, generation after generation. An individual organism does not evolve during its lifetime. It is the population that evolves as advantageous traits become more common over successive generations. The mechanism through which much of this change occurs is natural selection, a concept illuminated by the brilliant minds of Charles Darwin and Alfred Russel Wallace. Imagine, if you will, a population of ancient creatures, perhaps early fish navigating the Paleozoic seas. Within this population, there is natural variation. Some might be slightly faster, some possess a slightly different fin shape, some might be better camouflaged. These variations are often heritable. That is, they can be passed down from parent to offspring. Now, picture the challenges these creatures face: predators, limited food, changing water temperatures. Not all individuals will survive to reproduce, and not all will produce the same number of offspring. Those individuals with variations that provide an advantage in their particular environment, perhaps the faster fish can escape predators more effectively, or the better camouflaged fish can ambush prey more successfully, are more likely to survive and pass on their advantageous traits. Over immense stretches of time, across countless generations, these small advantages accumulate. The population gradually shifts, becoming better suited or adapted to its environment. This is natural selection in action. The environment selects for certain traits, not consciously, but through the differential survival and reproduction of individuals. We see the profound evidence of this process etched into the very stones that comprise our planet's memory. The Cretaceous fossil record is perhaps the most direct and compelling testament to evolution. It offers us a series of snapshots, sometimes beautifully complete, sometimes tantalizingly fragmented, of life's journey through deep time. Consider the remarkable story of Diasem, whale evolution. If you were to look at a modern whale, you would see a creature perfectly adapted to aquatic life, streamlined and powerful. Yet the fossil record reveals its terrestrial origins. We find a sequence of fossils, starting around 50 million years ago, showing creatures like Pachycetus, a wolf-like mammal with ear structures remarkably similar to modern whales, but clearly adapted for land. Then come forms like Ambulocetus, the walking whale, with strong limbs for both land and water, and a long powerful tail. Later, Rhodhocetus shows even greater aquatic adaptations, with smaller hind limbs and a more whale-like body. Finally, creatures like Basilosaurus, though still possessing tiny vestigial hind limbs, are fully marine, their forms strikingly similar to early whales. This is not a sudden transformation, but a gradual, step-by-step modification, meticulously documented in the geological layers. Each fossil is a chapter in a long evolving story, illustrating descent with modification over millions of years. Another iconic example is Archaeopteryx, often hailed as a transitional fossil. Discovered in the late 19th century, this ancient creature, dating back about 150 million years, beautifully blends reptilian and avian features. It possessed feathers and wings, much like a bird, but also a long bony tail, teeth in its jaws and claws on its wings, reminiscent of small theropod dinosaurs. Archaeopteryx provides powerful evidence for the evolutionary link between dinosaurs and birds, a bridge connecting two seemingly disparate groups. Beyond these striking individual examples, the fossil record reveals broader patterns of evolution. We observe adaptive radiation, a phenomenon where a single ancestral species diversifies rapidly into many new forms, each adapted to exploit a different ecological niche. This often follows a major environmental change or a mass extinction event, which clears the ecological playing field. For instance, after the extinction event that ended the reign of the dinosaurs, mammals, previously small and overshadowed, underwent an explosive adaptive radiation, diversifying into the vast array of forms we see today, from bats to whales to primates, filling the newly available niches. We also see the evidence for speciation, the process by which new species arise. This often occurs when populations become geographically isolated, perhaps by a rising mountain range or a shifting river. Over vast periods, the isolated populations experience different environmental pressures and accumulate different mutations, leading to distinct evolutionary paths. Eventually, they become so genetically different that they can no longer interbreed, and a new species is born. The fossil record, though often incomplete, provides instances where we can trace these divergences, observing subtle changes accumulating over time within distinct lineages. The study of comparative anatomy further corroborates the story told by fossils. When we examine the skeletal structures of different species, we often find underlying similarities, even if the outward forms are vastly different. Consider the pentadactyl limb, the five-fingered limb found in humans, bats, whales, and many other vertebrates. Despite their diverse functions, grasping, flying, swimming, the basic bone structure is remarkably similar. This homology points to a shared ancestry, a common blueprint that has been modified over evolutionary time to suit different purposes. The fossil record allows us to trace the evolution of this fundamental limb structure, showing how it adapted as early tetrapods moved onto land, and how it diversified into the wings, flippers, and hands we see today. While paleontology provides the historical narrative, modern science, particularly molecular biology, offers an astonishing confirmation of evolution's grand tapestry. The genetic code, carried in DNA, is shared by all known life on Earth. By comparing the DNA sequences of different species, we can reconstruct their evolutionary relationships with incredible precision. The more similar the DNA, the more recently two species shared a common ancestor. These molecular phylogenies, evolutionary trees based on genetic data, consistently align with the relationships inferred from the fossil record and comparative anatomy. It is as if the Earth's most profound diary, fossils, is being cross-referenced with the very instruction manual of life, DNA, and they tell the same magnificent story. And let us not forget the profound role of extinction in the evolutionary saga. Extinction is not merely an unfortunate end. It is a natural, ongoing process, a vital part of life's dynamic dance. Most species that have ever lived are now extinct. This background extinction is a constant pruning of the tree of life, making way for new growth. But then there are the moments of profound global upheaval, the mass extinctions, which we touched upon in our exploration of the geological timescale. These catastrophic events, whether caused by asteroid impacts, massive volcanic eruptions, or dramatic climate shifts, wipe out vast numbers of species, resetting the evolutionary clock, as it were. While devastating, mass extinctions also create unparalleled opportunities for the survivors, leading to bursts of adaptive radiation and the emergence of entirely new dominant forms. The disappearance of the non-avian dinosaurs, for instance, paved the way for the age of mammals. So as we contemplate the fossils unearthed from ancient strata, we are not just looking at static remnants of a bygone era. We are witnessing the tangible evidence of life in motion, a continuous, branching, and adapting lineage stretching back billions of years. Each fossil is a testament to the power of evolution, a whisper from the past that speaks of struggle, adaptation, survival, and the endless capacity for change. This understanding of evolution provides the crucial lens through which we interpret every discovery in paleontology. It allows us to connect the discrete points in the fossil record into a coherent, flowing narrative, revealing the magnificent story of how life has transformed, diversified, and persevered on our ever-changing planet. It connects us, every one of us, to the deepest reaches of Earth's history, reminding us that we are but a tiny recent twig on that immense and ancient tree of life. As we continue our journey through the Dreamy Academy, let this understanding of evolution be our guiding star, illuminating the path as we delve deeper into the specific chapters of Earth's living past. For it is within this framework that the true wonder and relevance of paleontology truly unfold. We have journeyed together through the immense stretches of deep time, tracing the subtle whispers of life preserved in stone. We have learned what a fossil is, how its age is measured with the precision of cosmic clocks and geological layering, and how the grand tapestry of Earth's history unfurls across eons. We have peered into the engine room of life itself, witnessing the ceaseless, beautiful dance of evolution and the profound, shaping power of extinction. Now, with these fundamental tools grasped firmly in our hands, we arrive at a new horizon. The questions shift. No longer are we asking what life is, when it existed, or how it changed. Now we ask, what were these worlds truly like? What was it to breathe the air, to feel the sun, to hunt and be hunted in a time before our own? How did the landscapes appear? What sounds echoed through ancient forests, and what intricate relationships bound the creatures that called these vanished places home? This is where the art and science of paleoecology, paleogeography, and paleoclimatology truly begin to illuminate the past. We are not merely collectors of bones, we are detectives of lost ecosystems, archaeologists of vanished continents, and meteorologists of ancient atmospheres. We seek to reconstruct, with as much detail as the fossil record allows, the living, breathing worlds that cradled the organisms whose silent remains we now study. It is a slow and thoughtful endeavour, akin to restoring a masterpiece from scattered fragments, each brushstroke informed by careful observation and profound imagination. Consider, if you will, the very ground beneath your feet, or the stone you might hold in your hand. This seemingly inert matter is, in fact, a profound archive. Sedimentary rocks, the silent chroniclers of Earth's surface, offer the first, most fundamental clues about ancient environments. Imagine a river carrying fine silt to a lake, or waves depositing sand along a primordial shore. Over immense spans of time, these sediments compact and cement, preserving not just the remains of organisms, but also the very conditions of their deposition. When we examine a sandstone, we might infer a beach, a desert dune, or a swift-flowing river, its coarse grains hinting at energetic currents. A shale, with its delicate, layered structure and fine particles, often speaks of tranquil, deep waters, perhaps a calm lake bed, or a deep marine basin where only the gentlest currents dared to tread. Limestones, rich in the calcium carbonate shells of ancient marine life, are the unmistakable signature of warm, shallow seas. Beyond grain size, we observe features like ripple marks, preserved undulations from ancient currents, cross-bedding, the angled layers left by migrating sand dunes or river channels, or even mud cracks, the telltale sign of a once wet surface that dried and hardened under an ancient sun. Each texture, each pattern, is a word in the Earth's most profound diary, whispering secrets of its past. But individual rocks, like isolated words, only tell part of the story. To truly understand a vanished world, we must look at the entire paragraph, the entire chapter. The fossil assemblages. It is not merely the presence of a single dinosaur bone or a solitary fern frond that captivates us, but the collective array of life found together. What other creatures shared that ecosystem? Were there tiny insects buzzing among the ferns? Did ancient fish swim in the same waters as shelled ammonites? By studying the co-occurrence of different species, we begin to piece together ancient food webs, predator-prey relationships, competitive interactions, and even symbiotic partnerships. We ask, who ate whom? Who competed for resources? What was the structure of this ancient community? This allows us to envision a vibrant, interconnected ecosystem, much like a living forest or coral reef today, rather than a mere collection of disparate organisms. And what of behaviour? How did these creatures move, feed, and interact with their surroundings? Here, trace fossils. Those remarkable echoes of ancient activity we first encountered become invaluable. A fossilized footprint is not just a mark in the mud. It is a direct record of locomotion, the weight and gait of an animal, perhaps even suggesting social behavior if multiple tracks are found moving in parallel. A burrow tells us about the substrate an organism lived in, its oxygen levels and its feeding strategies. Coprolites, fossilized feces, offer direct insights into the diet of an ancient creature, revealing whether it was a herbivore, carnivore, or omnivore. These traces are not just remnants of bodies but ghost images of life as it was lived, offering a rare glimpse into the dynamic actions of long-extinct beings. The foundation of any ecosystem, particularly on land, is its plant life. Paleobotanical evidence is thus crucial for reconstructing terrestrial environments and climates. The morphology of fossil leaves, for instance, can be a powerful indicator of ancient temperatures and precipitation. Leaves with smooth, entire margins are more common in warm, wet tropical climates, while those with serrated or toothed edges tend to dominate cooler, temperate zones. Fossilized pollen and spores, microscopic and remarkably durable, are carried by wind and water across vast distances, providing a widespread record of ancient vegetation types, forest compositions, and prevailing rainfall patterns. Even the growth rings in fossil wood can reveal seasonal variations in ancient climates, much like the rings of a living tree tell us about its annual environment. By studying these green architects of the past, we can rebuild ancient forests, swamps, and grasslands, imagining the very air they purified and the shade they cast. Beyond the visible forms, the invisible language of chemistry whispers secrets from the stone. Isotope analysis of fossilized remains and surrounding rocks provides remarkably precise data on ancient temperatures, diets, and even migration patterns. For instance, the ratios of oxygen isotopes, specifically oxygen-16 and oxygen-18, preserved in the calcium carbonate shells of marine organisms or the phosphate of vertebrate teeth, can act as ancient thermometers, revealing the temperature of the water or the body fluids of the animal when it was alive. Similarly, carbon isotope ratios, carbon-12 and carbon-13, can indicate the type of plants an animal consumed, distinguishing between different photosynthetic pathways and providing clues about ancient food webs. Strontium isotopes found in teeth and bones can even track the geographical movements of ancient animals, showing if they migrated across different geological regions. These chemical signatures, often minute, unlock profound insights into the physiological and environmental conditions of deep time, and what of the very ground itself? Paleosols, or fossilized soils, offer direct evidence of ancient terrestrial environments, just as modern soils reflect the climate, vegetation, and topography of a region. Ancient soils preserve root traces, characteristic horizons, and mineral compositions that allow us to reconstruct past land surfaces. A paleosol might tell us if an ancient landscape was arid or humid, forested or grassy, stable or prone to erosion. They are the actual fossilized ground upon which ancient creatures walked, providing an intimate connection to the very earth of lost worlds. As we expand our view beyond local ecosystems, we must consider the grand stage upon which life's drama unfolded. The moving continents. Paleogeography is the study of historical geography, charting the slow, inexorable dance of Earth's land masses and oceans across geological time. Imagine, if you will, the continents drifting like rafts on a vast molten sea, coalescing into supercontinents and then fragmenting again, opening and closing ocean basins, pushing up mountain ranges. This constant rearrangement, driven by plate tectonics, profoundly influenced global climates, ocean currents, and the distribution of life. How do we know where the continents were millions of years ago? The evidence is multifaceted. The distribution of identical fossil species on now separate continents, such as the fern Glossopteris, found across South America, Africa, Antarctica, India, and Australia, was a key piece of evidence for the ancient supercontinent Gondwana. Furthermore, the magnetic signatures locked into ancient rocks, known as paleomagnetism, reveal the orientation and latitude of land masses at the time of their formation. By matching geological formations and rock types across continents, we can piece together their original positions, slowly animating the vast shifting maps of deep time. The movement of continents, the rise and fall of mountain ranges, and the opening and closing of ocean basins directly influence our next crucial area of study. Paleoclimatology, the investigation of ancient climates. Was the Mesozoic era truly a time of global warmth, allowing dinosaurs to thrive even near the poles? Was the Carboniferous a period of vast, humid swamps, giving rise to immense coal deposits? The tools of paleoclimatology draw from all the evidence we've discussed. Oxygen isotopes in marine fossils tell us about sea surface temperatures. The prevalence of smooth-margined leaves in a fossil flora points to warmer, wetter conditions. The discovery of evaporate deposits such as ancient salt beds indicates arid, desert-like environments. Conversely, the presence of glacial till and striations on ancient bedrock unequivocally signifies past ice ages. The distribution of temperature-sensitive organisms like corals, which require warm, shallow waters, or certain types of reptiles, whose activity is tied to external temperatures, helps to delineate ancient climate zones. By synthesizing these diverse lines of evidence, we can reconstruct the global atmospheric and oceanic circulation patterns of the past, understanding the grand climatic cycles that have shaped our planet and its life. Ultimately, all these threads, the sedimentary story, the ancient communities, the behavioral echoes, the botanical landscapes, the chemical whispers, the shifting continents and the breathing climates, are woven together by the paleontologist. We do not study paleoecology, paleogeography, and paleoclimatology in isolation. Instead, we integrate them, creating a holistic, dynamic, three-dimensional picture of vanished worlds. Each fossil, each rock layer, each chemical signature contributes a vital piece to a colossal puzzle that spans billions of years. Why do we dedicate ourselves to this meticulous reconstruction? Beyond the sheer wonder and intellectual curiosity, there is a profound purpose. By understanding how life and Earth interacted in the past, how ecosystems responded to dramatic climate shifts, continental reconfigurations, and mass extinctions, we gain invaluable insights into the resilience and vulnerability of life itself. The Earth has breathed differently many times before, and life has adapted, diversified, and persevered. By studying these ancient responses, we can better understand the challenges and potential pathways for life in our own rapidly changing world. It is a humbling and illuminating endeavour, reminding us that we are but a brief chapter in an epic, ongoing story. So, let us now carry these tools of reconstruction forward. As we begin to explore specific geological periods in more detail, I invite you to not merely memorize names and dates, but to imagine these worlds. Picture the light, feel the ancient air, hear the sounds, and witness the incredible diversity of life that has graced our planet. Let us step, with quiet reverence, into these magnificent, long-lost landscapes. Having journeyed through the vast epochs of geological time, charted the currents of evolution, and learned to decipher the intricate tapestries of lost worlds, we now arrive at a pivotal point in our exploration. We have spoken of the whispers in stone, of the Earth's grand clockwork, and the ingenious methods by which we reconstruct the lives and landscapes of the deep past. But how, you might wonder, do these whispers first reach our ears? How do we find these invaluable fragments of history, these silent witnesses to life's enduring saga? This chapter, dear friends, invites us into the very heart of the paleontological endeavour, the field and the laboratory. It is here that the grand theories meet the grit and dust of reality, where the abstract concepts we have discussed take on tangible form. It is a journey that marries rigorous scientific method with the patient art of discovery, a blend of detective work, physical endurance, and an almost reverent sensitivity to the Earth's ancient narratives. So let us imagine ourselves stepping out of the tranquil halls of our dreamy academy and into the sun-drenched badlands, the wind-swept cliffs, or the quiet riverbeds where the Earth unveils its most precious secrets. This is where the hunt begins, a quest for knowledge that demands both a discerning eye and an enduring spirit. Where does one even begin to look for something as rare and ancient as a fossil? It is not merely a matter of digging anywhere. Indeed, such random excavation would be fruitless, even destructive. Our search is guided by the fundamental principles we have already laid down. We know that fossils are almost exclusively preserved in their sedimentary rocks, those layers of compressed sediment, laid down by water, wind, or ice, which gently cradle the remains of life within their strata. Igneous rocks, born of fire, and metamorphic rocks, transformed by heat and pressure, typically offer no such refuge. Thus, our first step is always to consult the Earth's own geological maps, veritable treasure charts that delineate the distribution of different rock types across the landscape. These maps, meticulously compiled by generations of geologists, steer us towards outcrops of shale, sandstone, limestone, and mudstone, the potential libraries of deep time. But even within these promising geological formations, not every layer holds a fossil. The relentless forces of erosion are our unwitting allies in this quest. Wind, water, and ice, patiently carving away at the Earth's surface, act as nature's own excavators, slowly stripping away the overburden to expose the fossiliferous layers beneath. This is why many significant fossil discoveries are made in places where erosion is particularly active. Arid badlands, where soft sedimentary rocks are sculpted into dramatic, often barren landscapes. Along riverbanks and stream beds, where flowing water constantly exposes new material. Or in road cuts and quarries, where human activity inadvertently slices through ancient strata. We walk these landscapes with a particular kind of reverence, our eyes trained not just on the ground beneath our feet, but on the subtle nuances of colour, texture, and form in the exposed rock. Sometimes, a discovery is born of pure serendipity, a hiker stumbling upon an exposed bone, a farmer unearthing a strange tooth. More often, however, it is the result of systematic prospecting, or surveying. Carefully walking transects across promising terrain, patiently examining every weathered surface, every scree slope, every small fragment that might hint at a larger treasure hidden within. It is a slow dance with the landscape, a quiet conversation between the present and the profound past. Imagine, if you will, the gentle crunch of gravel underfoot, the vast silence of a remote badland broken only by the whisper of the wind. You're walking, your gaze sweeping across the eroded gullies and sun-baked slopes, searching. What are you looking for? Not a complete skeleton, not at first. Often it is a mere fragment, a sliver of petrified bone, a telltale tooth, a peculiar texture in the rock that doesn't quite match its surroundings. These are the first whispers, the first invitations. When such a hint appears, the heart quickens, but the movements remain deliberate, unhurried. We drop to our knees, pulling out our hand lens, our small geological hammer, our compass, and our GPS. This initial assessment is critical. Is it indeed a fossil? What type of rock is it embedded in? What is its orientation? Are there other fragments nearby? We meticulously record the location, take photographs, and make detailed notes in our field journals. This is akin to a detective arriving at a scene, carefully documenting every detail before anything is disturbed. The paleontologist's toolkit in the field is a testament to both simplicity and precision. Beyond the essential mapping and recording instruments, it includes a range of tools designed for careful excavation, rock hammers and chisels for breaking away larger, unproductive rock, picks and shovels for moving overburden, and, for the more delicate work, dental picks, small brushes, and even paintbrushes. We also carry plaster, burlap, and aluminum foil, the materials for protecting our finds. If the initial prospecting reveals a significant fossil, particularly one that is largely still embedded in the rock, the site transforms into a full-scale excavation. This is where the meticulous planning truly begins. Permissions must be secured, often from landowners or government agencies. Logistics must be arranged. Water, food, shelter for the team, and, crucially, the means to transport the fossil once it is ready. Safety is paramount, especially in remote or challenging terrain. The first phase of excavation involves removing the overburden, the layers of unproductive rock and soil that lie above the fossil-bearing stratum. This can be back-breaking work, often done with shovels, picks, and even small mechanical diggers if the site permits. But as we approach the fossiliferous layer, the work becomes increasingly delicate. We begin to use smaller tools, carefully scraping away the matrix, the surrounding rock, millimetre by millimetre. The goal is not to extract the fossil immediately, but to expose it, to understand its full extent and orientation within the rock. Imagine a sculptor, slowly revealing the form hidden within a block of stone, but with the added constraint that the stone itself is as precious as the form it contains. Every stroke, every brush of dust is performed with utmost care. As the fossil begins to emerge, we create a detailed map of the site, marking the exact position of each bone or fragment. Photographs are taken from multiple angles at various stages of exposure. This documentation is vital as it allows us to reconstruct the original context of the find, offering clues about how the animal died, how it was buried, and what other organisms might have been present in its ancient environment. This is the essence of just taphonomy, the study of how organisms decay and become fossilized. When the fossil is sufficiently exposed but still largely embedded in its protective matrix, it is time for jacketing. This process is designed to protect the fragile specimen during transport. We first harden any exposed bone with a consolidant, a thin glue or resin that soaks into the porous material. Then, layers of wet paper or aluminum foil are placed directly over the fossil to create a barrier. Finally, strips of burlap soaked in plaster are carefully applied, building up a protective shell around the fossil and its surrounding rock. This plaster jacket, often resembling a giant cocoon or a plaster cast for a broken limb, is then allowed to harden. For very large fossils, multiple jackets may be created, or the entire block of rock might be undercut and encased. Each jacket is painstakingly labelled with the site name, date, and contents. Once the plaster jacket is dry and stable, the next challenge emerges, transporting these often massive and incredibly heavy packages from the remote field site to the laboratory. This can involve anything from carrying them out by hand, using ATVs or pack animals, to employing helicopters or specialized vehicles for truly monumental finds. It is a logistical puzzle, but one always undertaken with the utmost care, knowing the immense scientific value held within each plaster-encased block. Upon arrival at the Paleontological laboratory, the real painstaking work of preparation begins. This is where the fossil, still largely obscured by its rocky tomb, truly comes to life. The plaster jacket is carefully opened, a process that can take hours or even days, as the preparator works with surgical precision to ensure the fossil within is not damaged. Then comes the task of matrix removal. This is often the longest and most labour-intensive part of the entire process. Using a specialised array of tools, air scribes, miniature jackhammers that vibrate rapidly to chip away rock, dental picks, scalpels, and even precisely directed chemical baths, the preparator meticulously removes the surrounding rock. This is a highly skilled craft, demanding immense patience, a steady hand, and a deep understanding of fossil anatomy and rock mechanics. A single fossil can take hundreds, even thousands of hours to prepare. Imagine the dedication, the quiet focus required to liberate a creature from its millions of years of slumber, one tiny flake of stone at a time. As the fossil emerges, it is often fragile and fragmented. Consolidation continues throughout the preparation process, with glues and resins applied to stabilize delicate bones and prevent further deterioration. Broken pieces are meticulously repaired, like solving a three-dimensional jigsaw puzzle where many pieces are missing. Sometimes missing elements are reconstructed, using casts from the opposite side of the animal, or by sculpting new pieces based on anatomical knowledge. Once prepared, cleaned, and stabilized, the fossil is ready for rigorous GIS study and interpretation. This is where the pieces of the puzzle begin to form a coherent picture, where the silent whispers transform into clear narratives. Researchers use a battery of techniques: detailed comparative anatomy, examining the specimen under microscopes, taking precise measurements, and comparing it to known species. Modern technology offers incredible insights. CT scans and other Kelmsy 3D imaging techniques allow us to peer inside the rock, revealing internal structures without physical destruction, or to create digital models for endless manipulation and study. Chemical analyses can provide clues about diet, environment, and even age. The ultimate goal of all this arduous work is to contribute to our collective understanding of life's history. The findings are meticulously documented, analyzed, and eventually published in scientific journals, sharing the new knowledge with the global scientific community. This publication allows other researchers to scrutinize the data, replicate analyses, and build upon the discoveries, forming the bedrock of scientific progress. Finally, the prepared fossil becomes part of a permanent, curated collection, housed in museums or research institutions. Here, it is safely stored under controlled conditions, catalogued, and made available for future study. A fossil is not merely an exhibit, it is a scientific specimen, a primary piece of evidence that will continue to offer new insights as new questions arise and new technologies emerge. From the first subtle hint on a sun-baked hillside to its place of honor in a museum collection, the journey of a fossil is a testament to human curiosity, perseverance, and the profound desire to understand our place in the vast, unfolding story of life. It is a journey that reminds us that the grand narratives of deep time are built, patiently and painstakingly, one whisper, one fragment, one careful brushstroke at a time. And in this slow, thoughtful adventure, we find not just scientific facts, but a deeper connection to the very pulse of our planet's ancient heart. We have journeyed together, you and I, through the foundational elements of paleontology. We have held the concept of a fossil in our minds, understood the deep pulse of time, charted the grand epochs of Earth's history, witnessed the relentless engine of evolution, learned to reconstruct lost worlds from whispers in stone, and followed the patient hands that coax secrets from ancient rock, from the field's dusty embrace to the quiet sanctity of the laboratory. Each chapter has unfolded a new layer of understanding, a new tool for our collective gaze into the profound past. Now, as we stand at this juncture, with specimens carefully prepared and catalogued, with data meticulously recorded, the real work of synthesis begins. For a fossil in isolation is but a single word in a boundless epic. Its true power, its deepest meaning, emerges only when it is placed within its proper context, when it converses with countless other fragments of life, both known and yet to be discovered. It is here, in the grand weaving together of these individual threads, that the magnificent tapestry of life on Earth unfurls before us. Consider, if you will, the quiet hum of a research institution, a place where the diligent work of Chapter 6 finds its ultimate purpose. Here, the prepared fossil is not merely an object, it is a data point, a crucial piece of evidence. Paleontologists, like master storytellers, gather these pieces. They compare the delicate architecture of an ancient shell to its modern counterparts, trace the subtle shifts in a vertebrate's bone structure across millions of years, map the distribution of specific plant remains across continents, and analyze the microscopic details of pollen grains that once drifted on long-vanished winds. Each comparison, each analysis, is a question posed to the past, and often a profound answer received. This is where the meticulous science of comparative anatomy truly shines, where the principles of stratigraphy, which we explored in our discussions of relative dating, guide our understanding of sequential change. We begin to see not just individual organisms but entire ecosystems breathing, adapting, and transforming through eons. We reconstruct ancient food webs, discerning predator from prey, plant eater from scavenger, based on fossilized teeth, stomach contents, and even fossilized droppings known as coprolites. We chart migration patterns, track the ebb and flow of ancient seas, and witness the slow, inexorable march of continental plates, carrying diverse biotas with them. The individual fossil, once a solitary whisper, now joins a chorus, singing the story of its entire community, its entire world. It is through this painstaking synthesis that we begin to trace the very branches of the tree of life. Paleontology, more than any other science, provides the tangible evidence for the vast, intricate web of evolutionary relationships that connects all living things. When we speak of evolution, as we did in Chapter 4, it is the fossil record that provides the most compelling, undeniable proof of life's continuous transformation. Imagine for a moment the incredible journey from water to land. We don't merely infer this transition, we witness it, fossil by fossil. We find the ancient fish with fleshy, finned limbs that hint at weight-bearing structures, creatures like Tiktaalik, whose skeletal anatomy represents a perfect mosaic between fish and early tetrapods. Then we discover the early amphibians, still tied to water but increasingly adapted for terrestrial life, their limbs growing stronger, their lungs more efficient. Each fossil is a stepping stone, a chapter in a biological saga that played out over millions of years, illuminating the incremental changes that allowed life to conquer new frontiers. Or consider the awe-inspiring origin of flight. From feathered dinosaurs, ground-dwelling and swift, to the iconic Archaeopteryx with its reptilian skeleton and unmistakable avian feathers, and then to the diverse array of early birds, the fossil record meticulously documents the evolutionary pathway. We see the gradual refinement of wings, the lightening of bones, the development of keeled sternums for powerful flight muscles. These are not leaps of faith, but carefully documented transformations, preserved in stone. Even the rise of our own lineage, the mammals, is a story written in ancient bones. From tiny, shrew-like creatures scurrying beneath the feet of dinosaurs, to the spectacular diversification that followed the great KPG extinction event, we trace the development of specialized teeth, the evolution of warm-bloodedness, the emergence of lactation, and the complex social behaviors often inferred from trackways and fossil assemblages. Paleontology allows us to peer back into the deep past and see our distant ancestors, humble and resilient, laying the groundwork for the incredible diversity of mammalian life we see today, including ourselves. This grand tapestry also reveals life's enduring resilience. The geological timescale, as we explored in Chapter 3, is punctuated by moments of profound crisis, the mass extinctions that reset the biological clock. Yet, what the fossil record consistently demonstrates is not merely destruction, but also the astonishing capacity for recovery and renewal. After each cataclysm, life, in its myriad forms, has found new pathways, diversified into newly opened ecological niches, and pushed the boundaries of adaptation. These are not merely stories of loss, but also of profound opportunity, of the dynamic interplay between catastrophe and creativity that has shaped the biosphere. The Permian-Triassic extinction, for example, wiped out over 90% of marine species, yet from its ashes arose the dinosaurs, a group that would dominate the planet for 160 million years. This cyclical pattern of diversification, crisis, and recovery provides a crucial context for understanding the inherent dynamism of life on Earth. And this perhaps is where paleontology speaks most directly to our present moment, offering profound insights into the challenges and opportunities we face today. Why does understanding deep time matter to you, here, now? Firstly, paleoclimate data, derived from fossils and the rocks that contain them, provides an invaluable long-term perspective on Earth's climate system. By studying ancient oceans and atmospheres, we can reconstruct periods of extreme warmth and frigid ice ages, understanding the planet's sensitivity to greenhouse gases, the dynamics of ocean currents, and the feedback loops that drive climate change. The fossil record shows us that Earth's climate has always fluctuated, but it also reveals the rates and magnitudes of change. This deep time perspective is absolutely critical for contextualizing current global warming trends, helping us to differentiate between natural variability and unprecedented anthropogenic impacts. The past, in this sense, becomes a vital guide for navigating the future. Secondly, paleontology profoundly informs our understanding of modern biodiversity and conservation. By studying past extinction events, both background and mass, we gain a clearer picture of the natural rates of species loss and the factors that drive them. This allows us to assess the severity of the current biodiversity crisis, often referred to as the Mostiscan, quote, 17 norm. Are current rates of extinction within the bounds of natural cycles, or are they orders of magnitude higher, signalling a crisis driven by human activity? The fossil record provides the baseline, the long view, against which we can measure our present impact and understand the long-term consequences of habitat loss, climate change, and other pressures on ecosystems. It teaches us about the interconnectedness of life, the fragility of ecosystems, and the long, slow process of recovery that follows significant biodiversity loss. Beyond these critical environmental applications, paleontology continues to inspire and inform in countless ways. It assists in the exploration for vital resources, as microfossils are often key indicators for petroleum and natural gas deposits. It fuels our imagination, inspiring art, literature, and film, reminding us of the incredible wonders that once walked, swam, and flew on this planet. And perhaps most profoundly, it offers a unique perspective on our own place in the cosmos. To understand 4.6 billion years of Earth's history is to grasp the relative brevity of our own species' existence, fostering a sense of humility, wonder, and perhaps a greater sense of responsibility for the living world we inhabit. The story, however, is far from complete. Paleontology is not a static field, but a vibrant, ever-evolving science. New discoveries are made almost daily, whether in remote badlands, deep ocean trenches, or even within the dusty drawers of museum collections, re-examined with fresh eyes and new technologies. Advanced imaging techniques like CT scans allow us to peer inside ancient skulls without damaging them, revealing brain structures and sensory organs. Molecular paleontology, though challenging due to the fragility of ancient biomolecules, holds the promise of unlocking genetic secrets from the distant past. Each new fossil, each new analytical tool adds another sentence, another paragraph to Earth's most profound diary. The narrative is continuously refined, challenged, and enriched. The journey of discovery never truly ends. And so, we conclude this initial exploration of paleontology fundamentals. We have equipped ourselves with the tools, the vocabulary, and the mindset to appreciate the immense, quiet conversation that transpires between the present and the deep past. We have learned to read the whispers in stone, to feel the pulse of deep time, and to understand the incredible, resilient, and ever-changing story of life on Earth. Carry this sense of wonder with you, this profound connection to the ancient world, for it is a gift that enriches every single breath you take. The Earth's diary remains open, always inviting us to turn the next page. And so we arrive at a crucial juncture in our shared exploration, a moment where the ancient whispers of stone truly begin to resonate with the hurried heartbeat of our present. We have journeyed through immense epochs, witnessed the slow dance of continents, and traced the intricate branching of the tree of life. We have seen how life adapts, how it thrives, and how sometimes it vanishes in the face of overwhelming change. Now let us turn our gaze from the distant past to the pressing now, for paleontology, in its profound wisdom, offers not merely a chronicle of what was, but a powerful lens through which to understand what is and perhaps what could be. Consider this: every breath you take, every landscape you behold, every living creature that shares this planet with you is a direct heir to the long, tumultuous, and utterly miraculous history preserved in the fossil record. We are not separate from this history. We are a vibrant, fleeting thread in its grand, unfolding tapestry. And as we face unprecedented challenges, a rapidly changing climate, a staggering loss of biodiversity, the lessons etched in stone become not just academic curiosities, but urgent dispatches from Earth's deep past. Paleontology, in essence, provides us with a living laboratory of planetary change. Have you ever wondered about the true scale of current climate shifts? The fossil record holds the answers to similar questions from eons past. We see epochs when the Earth was a greenhouse world, devoid of polar ice, where palm trees swayed near the poles, and atmospheric carbon dioxide levels soared far beyond anything we experience today. And we see icehouse worlds, locked in glacial grip, where vast sheets of ice scraped across continents. We can study the rates at which these changes occurred, the biological responses they elicited, who thrived, who struggled, who ultimately disappeared. We can analyze ancient ocean currents, atmospheric compositions, and global temperatures, all reconstructed from a mosaic of fossil evidence and geological data. This deep time perspective offers invaluable context, helping us distinguish between natural cycles and the unprecedented acceleration of change driven by human activity. It reveals the inherent sensitivity of Earth systems and the profound ripple effects that even seemingly small shifts can initiate across entire ecosystems. And what of the spectre of extinction? The fossil record, in its stark honesty, chronicles not one, but 5 great mass extinctions, moments when the living world was catastrophically reset. Imagine, if you will, the Permian Triassic extinction, often called Certus Quotosus 18, which saw an estimated 90% of marine species and 70% of terrestrial vertebrate species vanish. We sift through the rock layers of that time seeking clues: massive volcanic eruptions, dramatic ocean acidification, widespread anoxia, the depletion of oxygen in the seas. We see the long, arduous road to recovery, the millions of years it took for biodiversity to rebound, and for new forms of life to fill the vacated ecological niches. These ancient catastrophes are not just cautionary tales, they are detailed case studies in planetary resilience and vulnerability. They illuminate the mechanisms of collapse, the patterns of survival, and the profound long-term consequences of rapid environmental upheaval. By understanding how life responded to these past traumas, we gain critical insights into the current biodiversity crisis, helping us grasp the potential trajectories of our own future. The very ecosystems we strive to protect today are, in many ways, echoes of their ancient predecessors. The intricate food webs, the symbiotic relationships, the delicate balances of predator and prey, these have been evolving and re-evolving for hundreds of millions of years. Paleontology allows us to peer into these lost worlds and understand the deep roots of ecological principles. It shows us how ecosystems are built, how they function, and how they can unravel. When we study the fossilized remains of ancient forests, coral reefs, or grasslands, we are observing the fundamental operating principles of life on Earth, providing a baseline against which to measure the health and stability of our modern world. This profound connection between past and present underscores a fundamental truth. Paleontology is rarely a solitary endeavour. It is a deeply interdisciplinary science, a vibrant crossroads where geology, biology, chemistry, physics, climatology, oceanography, and even computer science converge. Geologists help us understand the rock formations, the stratigraphy, the tectonic forces that shape the Earth. Biologists lend their expertise in anatomy, physiology, and evolutionary theory to interpret the forms and functions of ancient organisms. Chemists analyze isotopes in fossil teeth or shells to reconstruct ancient diets and temperatures. Physicists contribute advanced imaging techniques to peer inside fragile specimens without damage. This collaborative spirit, this weaving together of diverse threads of knowledge, is what allows us to construct such a rich and comprehensive picture of Earth's history. We are, in a very real sense, all working together, each discipline offering a unique lens through which to view the grand, unfolding story of life. And what of the road ahead? If the past has been a story of astonishing discovery, the future of paleontology promises to be even more exhilarating. We stand on the cusp of a new era, powered by technological advancements that are revolutionizing how we find, study, and interpret fossils. Imagine, for instance, a world where fragile specimens need not be physically broken open to reveal their secrets. This future is already here, thanks to advanced imaging techniques. CT scanning, familiar from medical diagnostics, allows us to create detailed 3D models of fossil interiors, revealing delicate brain cases, internal ear structures, or even the last meal of an ancient creature, all without touching the specimen. Even more powerful are synchrotron facilities, which use incredibly bright X-rays to image fossils at a microscopic level, unveiling cellular structures or the precise composition of fossilized tissues. These tools are opening up entirely new realms of inquiry, allowing us to understand the soft tissues and internal anatomies that were once thought to be permanently lost to time. Then there is the tantalizing, though often challenging frontier of molecular paleontology. The dream of recovering ancient DNA from dinosaur bones remains largely elusive, but we are making strides. The focus has shifted to more robust biomolecules like ancient proteins, which can survive far longer than DNA. Techniques like proteomics are allowing scientists to extract and sequence fragments of proteins from exceptionally preserved fossils, providing new phylogenetic data and even insights into the physiology of extinct organisms. Imagine understanding the precise composition of an ancient collagen or keratin, linking a fossil directly to its living relatives at a molecular level. Computational paleontology is also transforming the field. We are building sophisticated computer models to simulate the biomechanics of extinct animals, how a Tyrannosaurus rex ran, how a pterosaur flew, how a saber-toothed cat bit. These models, fed by detailed anatomical data from fossils, allow us to test hypotheses about locomotion, feeding strategies, and even the sensory capabilities of creatures long gone. Furthermore, vast databases of fossil occurrences and environmental data are being analyzed with powerful algorithms to reveal large-scale patterns in evolution, extinction, and biogeography that were previously invisible. Beyond the lab, the field itself is being transformed. Remote sensing technologies like LiDAR, light detection and ranging, are being used to map landscapes and identify potential fossil-bearing outcrops in remote or heavily vegetated areas, allowing paleontologists to prospect more efficiently and safely. Drones equipped with high-resolution cameras can survey vast terrains, creating detailed geological maps and identifying promising localities from the air. And let us not forget the enduring human element. The future of paleontology also lies in the new frontiers of exploration, untapped regions of the world, deeper delves into microfossil records, and the continued search for the earliest evidence of life on Earth, perhaps even connecting to the nascent field of astrobiology as we ponder the potential for life beyond our planet. Citizen science is also playing an increasingly vital role, with amateur enthusiasts making significant discoveries and contributing to data collection and analysis, fostering a broader community of discovery. As we bring this journey to a gentle close, we hope you feel not overwhelmed but rather invigorated by the vastness and wonder of it all. Paleontology is more than just the study of old bones. It is a profound meditation on time, on change, on the enduring resilience and breathtaking diversity of life. It is an invitation to humility, reminding us of our fleeting moment in the grand cosmic drama, and a call to action, urging us to be mindful stewards of the living world we inhabit. The Dreamy Academy has offered but a glimpse, a quiet opening of a window onto an infinite landscape of discovery. The tapestry of life continues to weave itself, each passing moment adding new threads, new patterns. And with every new fossil unearthed, every ancient secret whispered from stone, we deepen our understanding of this extraordinary planet and our own intricate place within its story. May your curiosity remain boundless, your imagination ever vibrant, and your heart open to the profound wonders that lie beneath our feet, waiting patiently to be discovered. This story of life is still unfolding, and we are all a part of it. We have journeyed together, haven't we? We have delved into the very essence of paleontology, peeling back layers of stone and time, deciphering the hushed whispers of ancient worlds. We have learned of the silent, slow dance of continents, the fleeting brilliance of life, and the vast, unblinking eye of deep time. We have seen how the earth keeps its most profound diary, etched not in ink, but in the very fabric of its being, waiting patiently for us to learn its language. And yet, as we stand here, gazing back at the path we've travelled, we must also acknowledge the boundless expanse that stretches before us. For every story we have unearthed, every mystery we have begun to unravel, countless others remain veiled, slumbering beneath miles of rock, waiting for their moment in the sun. The unresolved mystery, the vast tapestry of untold stories still hidden within Earth's geological record, is not merely a challenge, it is an invitation. It is the very heart of paleontology's enduring allure, the promise of discoveries yet to be made, paradigms yet to be shifted. Consider, if you will, the very act of discovery itself. It is not a static event, a singular moment of revelation, but rather an ongoing, iterative process. What we understand today as fundamental truths in paleontology are often the culmination of generations of inquiry, built upon the insights and sometimes the misinterpretations of those who came before. Think of the earliest conjectures about fossil remains, dragons, giants, mythical beasts, slowly giving way to scientific understanding. Each new find, each refinement of dating techniques, each technological leap adds another brushstroke to the ever-evolving portrait of ancient life. The field, you see, is not a finished book, but a living, breathing narrative, constantly being written and rewritten with every new piece of evidence. This dynamic nature is what makes paleontology so profoundly exhilarating. There are no ultimate answers, only increasingly refined questions. A fossil unearthed tomorrow might entirely reshape our understanding of a particular lineage, a mass extinction event, or even the very mechanisms of life's evolution. We have witnessed this time and again. The discovery of feathered dinosaurs transforming our view of their avian descendants, the intricate details revealed by molecular paleontology, overturning long-held assumptions about evolutionary relationships, the deep-sea vents showing us that life could thrive in conditions once thought impossible. The Earth, in its infinite wisdom, holds surprises beyond our current imagination, patiently awaiting the curious mind, the diligent hand, the discerning eye. What then does it mean to engage with such a field? It requires not only scientific rigour and meticulous observation, but also a profound capacity for imagination. When we study a fossilised bone, we are not merely examining a piece of mineralised tissue, we are peering through a window to a creature that once breathed, moved, hunted, and perhaps even loved under skies and suns that were profoundly different from our own. We reconstruct entire ecosystem from fragments, infer behaviour from trace fossils, and deduce climate from the subtle chemistry of ancient soils. This act of imaginative reconstruction, grounded in scientific evidence, is what truly brings the past to life. It is an art as much as it is a science, a synthesis of data and vision. And this synthesis extends beyond the individual paleontologist. Paleontology, as we have seen, is inherently interdisciplinary. It draws upon geology for understanding rock formations and stratigraphy, chemistry for isotopic analysis, physics for dating and imaging, biology for comparative anatomy and evolutionary theory, and even computer science for modelling ancient climates and ecosystems. It is a testament to the interconnectedness of all knowledge, a grand collaboration across the scientific spectrum. To truly understand a fossil, one must often consult with a geochemist about its elemental composition, a botanist about the ancient flora that surrounded it, and a climatologist about the atmospheric conditions of its time. We are all, in essence, weaving a single, intricate tapestry of understanding. But the journey through deep time offers more than just scientific knowledge. It offers a profound shift in perspective. When you truly grasp the immense scale of geological time, when you internalize that humanity's entire recorded history is but a fleeting flicker in the vast cosmic year, your understanding of your own place in the universe inevitably transforms. The anxieties of the present, the urgencies of our daily lives, while still vital, begin to nestle within a larger, more enduring narrative. You become acutely aware of the incredible resilience of life itself, its capacity to adapt, to diversify, to persist through cataclysmic change. This perspective, this deep time lens, is not meant to diminish our present concerns, but rather to contextualize them. It underscores our responsibility to the planet and to future generations. If life has endured countless extinctions and dramatic climate shifts, what role do we play in the current moment? Paleontology doesn't just tell us what happened. It offers critical insights into how the Earth system responds to change, how species adapt or perish, and what the long-term consequences of environmental upheaval can be. It is a mirror reflecting our past, allowing us to glimpse potential futures. So, what lies ahead for this slow and thoughtful adventure? The future of paleontology is as boundless as the past it seeks to uncover. We will undoubtedly see even more sophisticated imaging techniques, allowing us to peer inside fossils without disturbance, revealing cellular structures or even molecular remnants with unprecedented clarity. Molecular paleontology will continue to push the boundaries, perhaps even extracting and sequencing ancient DNA from increasingly older specimens, offering direct genetic links to long-extinct organisms. Computational modelling will grow in power, creating ever more realistic simulations of ancient worlds, allowing us to test hypotheses about predator-prey dynamics, migratory patterns, and the spread of ancient diseases. Yet, beyond the technological advancements, the true future of paleontology lies in the questions we dare to ask. How did the very first complex multicellular life arise? What were the true drivers behind the Cambrian explosion, that sudden burst of biodiversity? What other lost worlds exist, perhaps beneath the ice caps or deep within unexplored geological basins? How do we better integrate our understanding of ancient ecosystems to inform modern conservation efforts? The questions are endless, each one a thread leading us deeper into the labyrinth of time. And what of you, dear explorer? Perhaps your journey with us has sparked a nascent curiosity, a quiet wonder about the world beneath your feet. Perhaps you now look at a simple stone, a patch of exposed rock, or even a bird soaring overhead with a renewed sense of connection to the deep past. That in itself is a profound achievement. For paleontology is not solely the domain of scientists in laboratories or field camps. It is a way of seeing the world, a recognition of the grand, interconnected story of life on Earth. We have traversed eons, witnessed the rise and fall of empires of life, and touched the very foundations of existence. We have learned that every single breath you take contains atoms that have been part of ancient oceans, primordial forests, and the very bodies of dinosaurs. You are, in a very real sense, a living, breathing chapter in Earth's ongoing story. As our shared journey through the fundamentals of paleontology draws to a close, we leave you not with the sense of completion, but with an open invitation. The Dreamy Academy may have guided you through these initial steps, but the vast, wondrous library of Earth's history is forever open. Continue to wonder, continue to question. Look at the world with the eyes of a paleontologist, seeing not just the present, but the echoes of countless pasts. For in every stone, every landscape, every living creature, there lies a story waiting to be heard, a secret waiting to be whispered across the chasm of deep time. The greatest discoveries, after all, are often made by those who simply choose to look a little closer and listen a little longer. Thank you for joining us on this slow and thoughtful adventure. The ancient world awaits your continued exploration.